a decoder has several input lines and several output lines. Remember we said that a multiplexer has multiple input lines and one output, but the DMUX has several output lines but one input line. So somehow we need functionality in which we have a device or a combinational logic circuit that allows us to have multiple inputs and multiple outputs, and that functionality is obtained from a decoder. So a decoder function is to detect a specified combination or code formed by the inputs. So the same way we were using the select lines to detect which input lines do we want to feed to the output. On the contrary, with the decoder, the select lines are absent, and therefore the combination of the required select lines becomes our two inputs. So for n input line code, decoder may have up to 2 to power n output lines. So for instance, we have 3 inputs that we are passing on to our decoder. We are saying that the output of the decoder may be up to 8, because that will be 2 to power 3 becomes 8 output lines. So one characteristic feature that you observe is not there in the decoder is the select lines, like they were there in both the multiplexer and the multiplexer. So for us to understand this better, we need to look at a binary decoder. And a binary decoder is the one that the ratio of input to output lines is given by this ratio, which is n to 2 to power n. This is known as the binary decoder. So sometimes you may have other decoders that are not following this ratio, and those are beyond the scope of our course. So we will concentrate on this binary decoder and illustrate how it works. So let us now consider the gate level implementation of such a 2-line to 4-line binary decoder. And since we have two logic variables A and B, then our outputs are going to be 4 combinations of codes that can be formed by the two variables A, B. Since we have said it is 2 to power 2, then our output lines are going to be 4, and clearly we know that if we have two variables A, B, they can have 4 possible combinations, such that 0, 0, 0, 1, 1, 0, and 1, 1. So we have 4 possible combinations of outputs that we can get from such a decoder, and those combinations are following this order, just like I have illustrated here. When we have 0, 0, that is equivalent to A bar, B bar, and 0, 1 is equivalent to A bar, B, A, B bar, and A, B. So those are the 4 possible combinations that our decoder may have, and therefore we say that such a decoder may be considered to be a generator of all the 4 possible main terms. Remember we said we can classify these code combinations or these binary combinations as M0, M1, all the way up to M3. So since now we have said that the outputs of a binary decoder are going to be given by Y0 is going to be given by A bar, B bar, Y1 is going to be given by A bar, B, Y2 is given by A, B bar, and finally Y3 is given by A, B. Then we can say that we can implement this binary decoder using gates, such that we have our Y naught being a combination of A and B, in which case A is getting inverted and B is getting inverted, and this becomes one output of a binary decoder, which is Y0. And similarly, you can implement Y1 again using an AND gate with the one inverter of A and B being uninverted. And similarly, we can describe the formation of the output Y3 as again coming from two inputs A and B that are not complemented or inverted. And this is a very simple way in which you can implement a binary decoder. and the only thing we are missing here is what we had seen earlier in terms of a chip in number for activating our decoder. Otherwise, this becomes the entirety in which a binary decoder. And now we will see how it is formed with the combination of a chip in number pin. So this is the formation of a binary decoder at the gate level, and you can see clearly, just like we have described, each of the 4 inputs is coming from an AND gate, and the 4 possible combinations of our inputs are either passing through the inverter or not passing through the inverter to get the required input. That is our gate level implementation of a binary decoder, and the symbol for the binary decoder is similarly what we did with either the multiplexers or the multiplexers, and you can see that it has 2 inputs, A, B. It has 4 outputs, Y0 to Y3, and it has 1 chip enable pin that allows us to turn this decoder on or off. Our best understanding of how the binary decoder works would be through an example. Therefore, we look at this example that says implement the following function using a decoder and external logic circuits. So our equation is given here that we have 2 outputs that we need, F1 and F2, and F1 is expressed as a function of 2 variables A, B, C, actually 3 variables A, B, C, and the same thing is formed from F2 output, and each of them has its own expression. So the best way we can do that is to express both F1 and F2 in terms of minterms, and this is rather straightforward. So we would just remember what we learned about expressing a Boolean expression using or in terms of its minterm, and we normally ask ourselves this first term, can you express it in terms of all the 3 possible variables? And therefore we have A bar, B bar, and then we say we can have C being in complement and not in complement. So this becomes our other possible term that is coming from this AB, plus this other term already is in full, but we have BC bar, and therefore we have another term here that is missing, that is A, and A may be either complemented or may be uncomplemented. Therefore we write it as such. Therefore we have 5 terms now, and we can now be able to encode them in the usual way we do with sum of product terms, such that we can say that 0, 0, whenever you have a complemented variable, you term that as a 0, and any term that is uncomplemented, you give it as a 1, and therefore this will be 0, 0, 1. This is 0, 0, 0, 1, 0, 1, 0, 1, 0, and 1, 1, 0. And we can clearly see that this is our minterm 1, minterm 0, minterm 5, minterm 2, and minterm 6. Therefore, we can say that our F1 is going to be given by sum of minterms. We arrange them in the order 0, 1, 0, 1, 2, 5, 6. And you can do it in a similar manner for F2. All we need first and foremost is to break the XOR operation into its constituent terms, which is always in this form. So this is, we normally say this is exclusive OR. It is true only when the 2 variables are not the same. So one is complemented, the other one is not complemented, and the same case on this side. And therefore, we can open now this bracket and say that F2 is going to be given by A, B bar. We can still apply the De Morgan's theorem like we learned. This is like that, and this is BC bar like that. When we open this term, this becomes A bar or B bar plus B bar or C bar. Therefore, when you open this term, we will just get something that takes the shape A B bar plus A bar B, and I repeat all of this. We have A bar or B bar or B bar or C bar. So what we know is that with this, we know that this relationship that says A dot A bar is equals to 0. And therefore, whenever we meet any two terms that are opposite of each other, then we normally term that term as 0. So we know we have A. Whenever we find A bar, this goes to 0. And we have B and B bar, this term goes to 0, as well as that term. So what are we left with? We are left with AB bar. Our F2 becomes AB bar. This one and this one are the same. Remember we said that B bar or B bar is equals to B bar. So you can just drop one of them, or A, B, this term and this term becomes C bar, or this term and this term becomes the same, and finally A bar, B, C bar. So we can again get these two terms to give us the minterms of F2, and we can simply see that if we add a C here, it may be C and C bar, and it may be a C and C bar. So what we will have from this is 1, 0, 1, that is a 5, midterm 5, 1, 0, 0, that is midterm 4, 1, 0, 0 is still taken care of, 0, 1, 0, that is midterm 2, and 0, 1, 1, that is midterm 3. So those two we have taken care of. That is the same thing we have here, 0, 1, 0. So what we can say clearly from what we have seen is that F2 is equals to midterms, sum of midterms 2, 3, 4, 5. So those are that is the first step that we follow. You express your functions in terms of or in SOP form, and then express it as sum of midterms, because we can now implement the midterms using a decoder. Now with this expression of midterms, all we can say is that a decoder can be used to implement midterms very easily, because the midterms are like going to act like the output lines, and our three variables act as our input lines. So this is what we refer to as 3x8 decoder. This is how we symbolize it. It has chip number, that is normally active row, like we met earlier, and therefore it has three inputs, A, B, and C. These are our three variables, and therefore what is the output are the midterms that we have seen. And because we are told to use an external gate, these are starting from 0, 1 to up to 7, then we can say that the first function F1 is obtained by ORing. You can see whenever we have sum of products, these are sum of these products that we have obtained, which are expressed in terms of midterms. We can just express an SOP by an OR operation, whereby we are fetching the midterms that are available in our function. So we say we'll pick the 0, the 1, the 2, the 5, and the 6. You take this through an OR gate, and this becomes your F1. And similarly, you pick the 2, 3, 4, 5 for the F2, and you end up with this becoming your implementation of that circuit. We have shown F1, therefore the F2 is following the same idea. It is picking 2, 3, 4, and 5, and that is how you would implement such a function using a decoder and the external gate. The external gates are our up to 5 input OR gate.